In the last lecture, we looked extensively at neural networks. Now I'm going to explain convolutional neural networks, which are a special case of neural networks. And it's these convolutional neural networks that Alex Krzyzewski used to win that competition in 2012, which started this deep learning boom. So the issue that we have with neural networks when we consider an image, and the reason that we use convolutional neural networks instead, is let's say we've got an image of a face, which is going to be height h and width w. What a neural network does is unfold this image into a vector, which is going to be of size height times w, like this, and just width 1. Right, so now every single one of these is going to be a pixel, and when we have this first hidden layer, each of these pixels is going to be connected to every single neuron. The problem is that with images, most of the relative information is going to be within a local field. So, for example, with this person here, what makes up a face? In this case, we've got eyes, a nose, and a mouth, and we want to be able to learn features which can recognize that this is going to be a face. So we want it to be able to learn what an eye is. We want it to be able to learn what a nose is. Okay? But the problem is that with neural networks, pixels that are very, very far away have the same connections as pixels that are very, very close. So let's say that these two pixels are the eye. So let's color this in, and say that that is this eye. So they're both connected to this neuron, but also so is this pixel and so is this pixel, which is going to be the top one and the bottom one. So how are we actually going to learn some of these representations like eyes and nose from this sort of network structure? And it turns out that it's quite difficult. So what convolutional networks are going to do instead is completely not worry about this fully connected structure, and we're going to learn instead a matrix like this. Usually this matrix is going to be a height of 3 and a width of 3, and this matrix is going to slide across the image like that. And then once it gets to the end, it's going to slide downwards and do exactly the same thing again and go across the image. And this makes sure that the network now is focusing mostly on local information rather than equating information that's quite distant from another. So this means that for a pixel here, it's going to give a lot of attention to pixels over here. Oops. So we know that these pixels are quite connected, but on the other hand, a pixel over here is going to have no interest in pixels that are down here, which is exactly what we want when we want to learn image features. So we put the image in at the start, and this is the first convolutional layer. This then becomes the second layer, We do some other stuff as well to process it in between. So maybe the actual convolution is just what's going on in green, and then we do additional stuff I'll talk about later, and then we do the same, and then we do more processing, and then more convolutions and more processing. So now there's this slightly additional question of why these convolutional parts in green are getting thicker. The reason for that is that we don't just learn one of these 3x3 kernels, we learn multiple of them. So ideally, when we start off, we're only going to be able to learn very, very simple things. But as we get further into the network, we're going to have one kernel or one filter which is going to be responsible for eyes. So there's going to be one of these in, let's say the one in green is going to be responsible just for detecting whether or not there's an eye in this image, and it's going to have a very high score if there's an eye, or it's going to have a very high score in this part of the image and this part, and then a low score everywhere else. And then in a different color we're going to have another kernel which is only going to focus on noses. So in navy blue we're going to learn a kernel which is going to be very good at identifying noses and very bad at everything else. The thing is, as we get deeper into this image, we're going to need more of these different types of kernels. So we can't learn eyes and noses directly. We just have very simple stuff like edges, so we don't need as many of those. As we get further through, the kernels become more specific and less general, so we're going to need more of those kernels. I'm going to explain what's going on in the following slides. Hopefully this will all be more clear as we go through. So let's start off with a very simple example, which is just going to be this number 7 that we've seen in the MNIST dataset. And instead of learning these kernels, we are just going to say, let's consider what happens when we deal with these edges, these straight lines, as an example. And we're going to start off really simple, so we're just going to consider this image as a 4x4 grid. So first we're going to look at a kernel which is a diagonal line. All we want to do is understand the similarity between this line and what's on the image. So hopefully you can see in all of these squares, which are mostly black, that there's going to be no similarity. Then in the squares that have got a diagonal line, where where the bottom of the number 7 is, that's going to have a very high similarity. So all that means is that these are going to be given a 0 in the output feature map, and these ones are going to be given a 1 in the output feature map. And then, just for this example, to keep everything simple, everything that is in between is going to be given a 0.5. Okay, so we just end up with this, what's called a feature map, which is going to be 1s in this diagonal and then 0.5s across and 0 everywhere else. And we do the same for other kernels. So again, we're going to have 0s across the top row. We're going to have 0s here. But now we're going to have 1s in these horizontal, where we get horizontal lines on the 7, and 0.5s where the 7 has a diagonal. And you can see with the third straight line, which is just going to be a straight line down, we will see something very similar. I've just called everything 0.5 just to give you an understanding. But hopefully now you can see that we have, in all these different feature maps, we have different representations of the number 7. So in the top feature map, we have a representation which focuses on the diagonal. In the second feature map, we have a representation that focuses on the horizontal. And in the final feature map, we just have a just a number 7 where everything is slightly unsure. And when we combine these things together and we know what these kernels are, that's how we understand that this is a number 7 when it comes to the final classification layer. It's all based on these new representations that we've learned from the initial image. So I do want to point out that it's a little bit more sophisticated than this in general. So I kept everything simple and just talked about this kernel jumping right the way across. In practice, it's not going to jump that far. It's going to only move to about here. And then again, the next step is it's going to move just here and it's going to slide all the way across. And again, exactly the same thing when we move downwards. It's not going to go, it's not going to go all the way down. It's instead going to go, it's not a very good drawing. It's going to go a little bit down and slide downwards as well. So this is a sliding window. So once we have these three representations, what we do is we convert them into a tensor, and this is going to form the next layer of your neural network. So we've considered this in terms of just looking at a 4x4 thing. I want to really explicitly have a look into what's going on. So this is the filter that we had before. I think it was in green. And what actually happens when we have this filter that we've suggested that we should look at. We haven't officially learnt it, but it's probably something that's going to be useful. Is this filter, this kernel, is 3x3, and it's going to be zeros across the top row, 1 across the middle row, and zeros across the bottom row. This is assuming that we've normalized everything so that it's between 0 and 1, or between -1 and 1, which we sometimes do. What we're going to have in the actual image is something very similar, where all these black boxes, if I switch color, all the black boxes are going to be zeros, and all the white boxes, all the white pixels are going to be 1. So if I just do this, you can see when we consider this green kernel, the horizontal row, all that's going to happen is we're going to put it here, and then we are going to do a multiplication of the pixel value by the kernel value. So this is 0 times 0, 0 times 0, 0 times 0, 0 times 1, 0 times 1, 0 times 1, 0, 0, 0. You can see that all of these are going to be zeros. So in this case, when we do all these multiplications, they're all going to be 0, and then we just add everything up. So we're going to add up lots of zeros, and the top left corner in the output is going to be a 0. And then we slide this along 1. So it comes to here, And again, we're going to multiply by, we can get rid of all these. We're going to multiply all these zeros by this kernel, which is again going to be 0. And you can see that that's going to be the case quite a lot along the top. So it gets interesting when we get to here. So now for this part of the image, once the kernel has moved to here, it's going to be, I'm going to fill this in very quickly. We're going to have 0, 0, 0, 1, 1, 1, 0, 0, 0 as the pixel values. And for the kernel, it's going to be exactly the same. So we're going to have 0 plus 0 plus 0 plus 1 plus 1 plus 1 plus 0, plus 0 plus 0 plus 0. So once we add all of this up, we're going to get a 3 here. And again, as we move across, there's going to be some more 3s. And the only other place that we are going to look for something similar is down here. So we're going to just get rid of the green. And we have exactly the same thing going on. So, 0. This one's going to be 1. I'm just going to call this 0. Sorry, that will probably be 1 as well. 0, 1, 0. Maybe this can be a 1. So when we're in this diagonal, we have 0, 0, 0. So this kernel is always going to stay the same across the whole image. 1, 1, 1, 0, 0, 0. So now when we do this step, it's going to be 0 plus 0 plus 0 plus 0 plus 1 plus 1 plus 0 plus 0 plus 0. So we've only got 2 ones here, so this is now going to be a 2. So we'll usually get 2s and 1s down here. And it's exactly the same thing for the horizontal, for the vertical and for the diagonal ones. So now for the diagonal, if we stay here, for the diagonal, I think we had that in blue before, which is unfortunate. But yeah, we again just move these numbers. I'm going to go for darker blue. We just move these numbers from this kernel to this spot, which is going to be 0, 0, 1, 0, 1, 0, 1, 0, 0. And now for the diagonal output in the feature matrix, for this, it was this spot that we're looking at. We get something slightly different. It's just going to be 0 plus 0 plus 1 plus 0 plus 1 plus 0 plus 1 plus 0 plus 0. So in this case now we get 3. So this is the same as before, where in the first kernel we had high values across the diagonal and high values across the horizontal and medium values down the diagonal. It's just going to be the opposite. We're going to get 3s over here and like 1s and 2s across here, and then 0s everywhere else. And it's very similar for the vertical kernel, where we just have a vertical line. This is going to be all like 1, 1, 1, 2, 2, 2, something like this, and then 0 everywhere else. And you can see that we have these kind of representations of the number 7 that are all slightly different, but you can see what's going on. So far I've just talked about images that are black and white or grayscale, where there's just the one channel. When we have it's quite similar when we have a color image, but remember that instead of just having one of these, we have the 3 channels. So you've got a red, green, and blue channel. And yeah, this is exactly the same as when we go into deeper layers. Instead of just having this 3x3 kernel that moves across the image, as I showed before, we're going to have a filter like this, which is now going to be a 3x3x3 filter for an RGB image, and that again is going to move across and down. And if we have in deeper layers where we have lots and lots of these channels, then this can just become C 3x3x C size filter. So it's just doing exactly the same thing, just added a different dimension. It's a little bit more complex. The important thing to note is that this convolution is still going to go only in two directions. It's only going to go across and then downwards. It's never going to go in this direction.